Okay, hi, thanks for that. Thanks also for hanging around to the end of the conference. I was worried there'll be nobody here. Thanks, Boumediene, also for organizing. And actually, some of this work is going to be talking about work that we've done together. Also, I'm happy to say that my university, GUST, has been a partial sponsor of this conference, and we're happy to have done that. So this talk is going to be actually quite different, perhaps, from what's many of the talks that have been going on, a bit of a higher level look at a different area. This is more like, we can see this talk more like as a sort of beginning of a new research area rather than a sort of an established field somehow that with lots of results. So I'm going to be talking about something called algorithmic probability, which is part of algorithmic information theory, and simplicity bias, which is kind of a real world adaptation of that. My trajectory has been rather odd. I started actually my master's with Professor Jerome Lamb in dynamical systems. I then went into biophysics, and now I'm sort of kind of coming back slightly. So I've done a bit of work recently, or a bit of machine learning and dynamical systems. So I'm going to jump straight in now with a motivational quote. So first of all, Marvin Minsky, hopefully many of you will be familiar with him. He's one of the sort of founders of artificial intelligence. He founded the MIT AI lab. He had a long career in computing, computer science, etc. And he passed away a couple of years ago, but just before that, at the end of his career, he had this to say about algorithmic probability. So he said, "It seems to me that the most important discovery since Gödel was the discovery by Chaitin, Solomonov, and Kolmogorov of the concept called algorithmic probability, which is a fundamental new theory of how to make predictions. It should be possible to make practical approximations that would make better predictions than anything we have today. Everybody should learn all about that and spend the rest of their lives working on it." Okay, so I'm trying to invite you into this area, which is some area that I've been working not my whole life, but maybe let's say 10 years of my life. Okay, so what is he talking about here? In order to understand algorithmic probability, we have to understand Kolmogorov complexity. So Kolmogorov, obviously a very famous mathematician. His name appears in many different areas. One of the last things he did in his life was look at how can we measure the information content or complexity of individual objects. I mean, for example, like a data file or a binary string or some actual fixed object, unlike Shannon information theory, which is measuring the complexity, you could say, of a distribution. So what he and also Chaitin and Solomonov came up with, which by now is quite a reasonable idea, I think, to the modern mind, is that we should measure the complexity of something by the length of the program that is required to generate it. Okay, so if I can make this certain data file by writing a short computer program in Python, let's say, that generates all this data, then presumably the data in that is not very complicated. It's just somehow simple. Whereas if to generate some particular pattern or outcome, I need to have many millions of lines of code, then somehow that is going to be probably a truly complicated pattern. So we're by now familiar with programming in Python and writing code and compressing files when we attach them to emails, etc. So this should be quite a kind of intuitive idea. But obviously, at the time in the 1960s and 70s when this was being developed, it was not it was not so familiar. Slightly more formally, Kolmogorov complexity is defined as the length of a shortest program that can produce some given output pattern, where U is a universal Turing machine. I'm not going to focus too much on these details. We can just think about it as being some generic computing device. A couple of examples. So this is a typical example. If we have Y is just a simple string 010101, this has got obvious simple pattern. Therefore, it's going to be compressible. We could write a code like print 01 n times or something or other. And so we can say that the complexity of this pattern is low. In contrast, Z here is just a random pattern, a random string of zeros and ones that I generated. Presumably, it's got no patterns in it. It's got no kind of structure in there that you can actually use to compress anything. And so therefore, the Kolmogorov complexity would be large. Okay, so this is a very brief overview of a massive field, but it's quite, the intuition is quite reasonable. Compressibility is a measure of complexity. Okay. So that's Kolmogorov complexity. What's it got to do with algorithmic probability? Well, it turns out that another important computer scientist, so Leonid Levin worked with Kolmogorov, and Leonid is very famous in computer science for NP completeness, and he is still working, I think, in Boston University now. Anyway, he's had a good long career of important contributions. and this is one of them. So what he showed is that if you get a computer program, a random computer program on a Turing machine, actually it has to be there are some details there, but a random computer program, and just look at what it produces, okay? So you can imagine closing your eyes and hacking away at Python and just pressing run and see what happens. Most of your programs are going to generate an error, but the ones that produce something, you can look at the probability of the different patterns that you produce. And what he showed is in this context, the probability is actually directly related to the complexity, okay, in a very simple, neat form. So basically what that means is, for example, 0, 1, 0, and 0, 1, which has got low complexity, is going to have a high probability because k is small, and some complicated pattern like z will have relatively exponentially lower probability. And this idea is called algorithmic probability. So algorithmic probability, what Marvin Minsky was talking about, is this idea of looking at the probability of objects based on their algorithms and the probability that an algorithm will generate that particular output. So this result is building on Solomonov, and actually Solomonov is attributed with inventing algorithmic probability. But and what's quite interesting to this community and also to my work now that it's coming back is that the original motivation for Solomonov was actually trying to come up with generic ways to predict. So how can we look at forecasting and prediction in an abstract setting? And actually through that question, they ended up coming into these things, into this kind of relation, and then coming up with Kolmogorov complexity. And now we're starting to come back to the original motivation. Okay, so this is a nice result. In fact, it's a very nice result, 50 years old. But it has problems if you want to try and apply it in the real world, like I have been looking at biology, or maybe in time series, or maybe in whatever it is. First of all, Kolmogorov complexity is actually formally incomputable due to the halting problem, meaning that if I give you some data file or something, you can't even in principle actually work out the complexity. Okay, so it's not a quantity that you can just calculate directly. Also, the theory involves a universal Turing machine, which again is not, you don't find them lying around, in the jungle in biology, or even in time series necessarily, or even dynamical systems necessarily. So, this is quite a strong, constraint, you could say. And also, it's got this as an asymptotic theory. It's got these order 1 terms that could in principle be large. And like we were talking about earlier on, sometimes there are cases where you can ignore, you can prove things in a certain regime, but they work in another setting. But here, at least, the proof is for up to an order 1 term, which could be huge. And maybe the complexity might not be huge in the real world practical situation, in which case, what are you going to do? So these are challenges. So what I did, this is actually from my PhD work, to be honest, but it was published a few years after, is we wanted to see, well, this idea is something very strong and very, making a very strong statement about probability and complexity. So maybe we can see something, in a more practical setting by making a few approximations and some assumptions and things. I was in a theoretical physics department, so we're happy with doing that, more happy than mathematicians. But anyway, so the result we came up with is this, what we call the simplicity bias bound. So what is it saying? It's basically saying that if you got some kind of input-output map where you can sample inputs randomly and they produce some kind of shapes or patterns, then under some conditions, we can expect to have this kind of relation where the probability is bounded above by 2 to the minus k. So k here with a tilde on top is like a real-world approximation, or rather estimation, of Kolmogorov complexity. And normally we use some kind of compression algorithm like Lempel-Ziv, etc. And obviously it's an upper bound rather than equality, which is a weaker relation, but that's what we could do. We've got a couple of constants here, a and b, which might vary between maps, but they don't depend on x. And actually, under certain circumstances, if we know the number of possible output shapes, we can actually predict a, and a is usually around about 1. So we don't need to worry too much about a and b. B is also typically can be argued to be roughly 0, but you can fit it to data if you need to. Okay, so the main idea here is to say, if you have some input-output map with some conditions, and the outputs are giving you some kind of shapes, you can randomly sample the parameters and look at the probability and the complexity of the shapes, and you should be able to have some kind of a bound here. So if you think about this, and what I want to try to sort of convey, there's actually a bit of magic here somehow, because what we're suggesting is that from looking at the shapes directly, you can actually say something about their probabilities. Okay, which sounds should sound kind of crazy, because the way that we normally estimate probabilities is, for example, sampling, just counting frequencies, maybe some kind of extrapolation or some machine learning methods, but we don't normally just look at shapes and go, I think the probability is this and the probability is that. Okay, so this is a kind of a magic which I'm now trying to hopefully bring this magic into other areas. But just to continue with the story from this paper, we tried this then on a bunch of different sort of mainly biological contexts. That's the work I was doing. So I'm going to start by looking at let's see if the pointer works. It does, but it points somewhere else. That's exciting. Okay, so let's start by looking at this graph here. We have log probability and then complexity across the bottom. Each dot is a different RNA structure, and here the input is going to be like a certain fixed length. Let's say you got 60 letters that correspond. It's a bit like DNA sequences, yeah? So you can imagine randomly sampling these DNA sequences. It's actually RNA, but it's basically the same. And then when you sample a sequence, it folds up according to biophysics rules into some shape. Okay, so you sample a sequence, you get a shape. You sample a sequence, you get a shape. And if you do that lots of times, you get a probability distribution over the shapes. So each dot corresponds to a different shape, and we can see highlighted up here is a relatively simple shape. It's kind of just like a long tail with a couple of loops in it, which has relatively high probability and relatively low complexity. And highlighted here, for example, is another one which has got relatively low probability and relatively high complexity, and you can see how the shape is kind of a bit more irregular and erratic. And you can see there's basically what we were looking for is a roughly linear upper bound on the probability of different shapes, and this slope was actually predicted from the theory itself. Okay, so that black line slope came from the theory, it's not fit. Okay, so we did something magic here, which is look at the shapes and estimate something about their probabilities. We also did that for another biological system. This is actually ordinary differential equation system of, I think, maybe 6 or something equations with 15 parameters. We randomly sample the parameters. You get some kind of concentration time profiles that come out of this. And basically you can see that so each dot is a different discretized pattern, and the probabilities and the complexities are following the same kind of idea here. Which is that there's roughly a linear upper bound, and more complex things tend to be less likely. And then the last one I'll go through here is the one over here, which is quite a nice example, quite cool. So this is L systems that comes from actually computer graphics. So I think in the old days when they wanted to have a computer graphics of like a bunch of trees, like a forest or something, they developed this system for an algorithm for growing trees. So like grow, branch, grow, or something like that, yeah? So you can randomly sample these instructions and you generate a bunch of different trees. And as you can see up here, you've got like a small, simple tree with high probability, low complexity, and a more erratic, crazy-looking tree with higher complexity and lower probability. Again, this slope here was predicted. And again, what we're doing here is saying, you just show me the tree, and I'll give you some idea about a bound on its probability, okay? Which again, I feel like is kind of magic. All right, you might have noticed, that many of these are, unlike Levin's relation, you've got a lot of these points which are somehow simple but with low probability, so they're actually somehow far from the bound, which we've studied, but I haven't really got time to go into too much here. So we recognize this, and we've studied this in a couple of papers, but I'm gonna skip over it for now. Yeah, so actually just the last example. This one was a bit more recent. We had a nice paper that was actually where we were taking the same kind of ideas, simplicity bias, and looking at natural proteins, as in the ones that are in your body and inside living systems, and also RNA shapes and also tile shapes that were used to model biological systems. And we had the same kind of, this paper actually got into a nice journal, actually got a lot of attention. It was covered by the New York Times and Le Monde, and Nature Reviews Physics highlighted it, etc. It got quite a lot of attention because we were somehow using the simplicity bias bound in like practical situation of biology. Just a little quick example again here. You can see how in these tile shapes, so each dot is a different tile shape that is used in biology for for sort of modeling protein quaternary structures, you can see how, again, the high probability ones tend to be regular and symmetric and simple, and some of the ones down here are like kind of crazy erratic looking with a roughly linear upper bound. Okay, so basically this is the kind of background that I've been working in the sort of biophysics world. But then what I was, partially from discussions with Boumediene and from other interactions as well, we wanted to think, well, this is not actually biological. It's not actually biology. It's just saying if you have a map which has certain conditions and you have some shapes, then you can somehow predict them, okay? So that kind of problem applies way outside of biology. So I want to now go back into sort of more relevant to your world and where I'm trying to get into now, which is to see how this might be useful in machine learning or dynamical systems somehow. So first of all, I want to point out that Solomonov, initially, the initial first workings where this was done was actually in his aim to try and come up with a generic way to predict sequences. So it's actually kind of fundamentally came from time series forecasting. I also want to highlight Markus Hutter, who is probably the main guy working on this. So he's got 2 books, one from 20 years ago, where he is arguing that algorithmic probability should be part of the sort of fundamental idea of a generic artificial intelligence. And then much more recently, actually just about a month ago, I think he had his second book here. And Markus Hutter and Boumediene and I are working on a couple of projects. So this is one area where in artificial intelligence and sequence prediction, we can use algorithmic probability. Another case a bit closer to home. So I didn't actually work on this paper, but this is using directly the simplicity bias bound, which I just described to you. It's from the same group that I was working in. So Guillermo Valle-Perez and Chico Camado and Ard Louis they used the simplicity bias bound to answer this question or try to address this question, which is very relevant to this community, which is why is it or how is it that deep neural networks can generalize so well? Okay, so this is a big sort of mystery. They seem to work, but people don't understand why do they work so well. And they had this work where they tried to invoke the simplicity bias bound to basically say that the neural networks are working, or part of the reason why they're working is because a simplicity bias is biasing them towards functions that are somehow simpler and somehow relevant to the real world. So this paper has been cited about nearly 200 times by now, and it's kind of attracted some attention and some discussion, so it's an interesting one to look at. Okay, back to work that I've done. I was visiting Caltech for a few months 2 years ago with Houman Ohadi, whose name has appeared a couple of times already in this conference. And I wanted to see if we could use this simplicity bias as like a prior in some way. Okay, it's kind of like saying, looking at the shapes, I've got some idea already about what their probabilities are. Can we use this as a prior in some kind of machine learning application? So this was like a toy example. It wasn't really trying to solve a real biological problem, but it's just to kind of play with this idea and see if we can do something interesting. So I thought, okay, let's try RNA classification. Okay, so you can imagine you've got some sequences, you've got some RNA shapes. You want to now say, okay, I've got some training data. You give me a new sequence. I want to try and correctly classify the sequence. I wanted to see if we could use this prior somehow to aid in this task. So basically, the idea was to think, well, in the case that we have very, very small training data, then maybe having a prior is going to help us here somehow. And this is, like I said, a sort of a toy example just to kind of see how this might work. So the first thing we wanted to do is to say, okay, my classes are going to be the different RNA shapes. I've got 17 shapes in this context. And I'm going to, first of all, try and predict their probabilities, which will then give me a way to predict the class probabilities, which then can help me do classification in the context of very small training data. So here is on the y-axis, you've got the true probability of the RNA shapes, or the class probabilities, you could say. And on the x-axis, you've got the prediction based on the sort of simplicity bias prediction. And you can see there's a pretty reasonable positive correlation there between the log probability, suggesting that we can get something from this prior. And then when we use this to do the multi-class classification accuracy, in the extremely small training data regime, we did manage to improve the accuracy in the way that we expected with the prior. So again, this is like a toy example. It doesn't solve any big problems in the world, but it's just to see how we could use the what's it called, the prior. Okay, so now going back to time series, which was actually in the title of the talk, but as I wrote the talk, I realized that time series were going to be slightly less involved. But anyway, so this is work that I did with Boumediene a couple of years ago. And we asked the question, is it possible to forecast a time series without having historical data? Now, when I mentioned that to somebody once, they laughed and they said, but that's astrology, just, predicting the future by looking at the stars or whatever it is. And this is not astrology, okay? I'm just saying something quite simple, which is that if we know from simplicity bias that there are certain patterns that are more likely than others, then if I say, here's a time series, try and forecast it without looking at any history, well, we have some kind of bias towards things that are more likely than others. Anybody who's worked in time series already knows that there are certain patterns that are kind of popular, like linear increase or exponential increase. That's kind of obvious. But we wanted to go beyond just sort of a vague, okay, that's likely, that's unlikely, and see if we can actually use the simplicity bias bound to say, well, actually, is this sequence or this sequence, more likely than, which one's more likely, or, does it kind of conform to the simplicity bias bound, or is it just something that's a vague connection between simplicity and complexity? Okay, so how do we test it? We went into the World Bank open data, just got a whole bunch of data, short time series of like, I think 15 or 20 or whatever it was, data points. We combined a whole bunch of data of different random things like HIV infections in Germany and just economic data and education data, whatever data was there. And then we did something rather coarse, but it's just, again, to sort of put things into the same framework that we have been studying, which is we can convert a real value time series into a binary string by just thresholding it somehow and saying high and low, or we also had a different way of thresholding, but this is just one example. You can then convert all of these different thousands of time series into binary strings, and then you can ask, what's the probability that this string appears? Yeah, and what's its complexity? Complexity again is easy to work out. We've done this before. We just compress it somehow, use a complexity measure, and then we can also ask about what's the probability. So then we just put it together in the plot and see what we can see. Okay, so do we see something like the simplicity bias plots that we did for the other cases? And I think this is quite a nice plot. Okay, I've cherry picked it from the paper. There's not all of them. They don't all look maybe as good as this, but there is, I think, there a pretty clear relation that somehow follows the same kind of pattern, same kind of pattern as the other ones that we saw in the other contexts of like biology and things. You can see that around about 11 bits of complexity, there's a whole bunch of values that are somehow above the bound. I guess that means that there's some kind of preference for some kind of patterns, or maybe an oversampling of some time series or whatever it is. I'm not totally sure, but basically the overall picture is kind of like similar to what we had. Okay, and then into dynamical systems. So this is like more recent work. We started to, we wrote a paper or two on dynamical systems. So it's not totally obvious how this might apply to dynamical systems, but one way that we thought about it is maybe to go, well, if you, the simplicity bias is to do with inputs and outputs. So how can I turn this into an input-output problem? What we thought about doing is saying, well, you could imagine that the starting value, x0, and the value of mu are like parameters that you can sample. They're like inputs. And then if you iterate the map for, let's say, 25 iterations, then you can digitize that. No, let's not do that yet. Then you can digitize that in some way or other, maybe similar to how we did time series, and therefore you get an input-output map. Okay, so this is not, the logistic map is not normally viewed as an input-output map, but I'm just playing around with this idea and seeing how far we can go with it and see if it shows us anything interesting. So we rewrite this as an input-output map, where input, like I described there, and the output is going to be some binary string that you get from coarse graining, or rather thresholding. Okay, so then we also studied a couple of other maps, Gauss map and sine map, but I don't have time for that, so I'm just going to look at this one. Okay, so what do we see then? We'll start with the panel A. Panel A, so in every case, we're sampling the initial value between 0 and 1, x0. But we sampled mu over different intervals to kind of get a better idea of different kind of patterns. The first one is where mu is sampled between 0 and 4, And you can see here that I think there's pretty decent simplicity bias there. Again, the black line is a kind of the slope is being predicted there quite well. And if you think about it, if you know the logistic map, which obviously everyone here does, you might say, well, it's obvious that simple things are going to be more likely because if you're sampling mu between 0 and 4, if mu is kind of like small, let's say less than 3, you're going to get trivial outputs. So I know we realize that, and we said that in the paper. We weren't trying to make a general relation between simplicity and probability. We wanted to see, does this map actually quantitatively follow the bound in a kind of somewhat precise way? And I would say that's pretty reasonable slope prediction there. And it's not just a vague connection, but it kind of fits the same pattern as simplicity bias. In the other panels, we have sampling in different regions. So we started to sample in the regions where there's more kind of chaotic or complicated behavior. And basically what happens is you can see that B and C, you still have pretty much simplicity bias. But what happens when mu is 4, this is interesting because basically what happens is you lose the bias, as in you lose the distribution becomes roughly uniform, so the probabilistic bias disappears, and the simplicity bias also disappears as well. So we've kind of got here like a system where you kind of tune or play with the simplicity bias, you can kind of kill it off or bring it back. So it's not totally obvious what the dynamical system sort of consequences of this. Like I was saying in the beginning of the talk, this is more like a new area that we're trying to explore to see if there's something kind of interesting going to come out of this. This is literally work published the other day. And so what are the dynamical consequences of this? It's not totally obvious, but I'm just trying to see whether this map or this simplicity bias is appearing in different places and whether we can make use of it in these other contexts. We also had a paper with Boumediene also, which was looking at the random logistic map and the logistic map again. So in this case, we just added a little bit of noise to the logistic map. And in this case, as long as the noise is not too big or too small, then we could have some kind of simplicity bias for even fixed values of mu. What we also did in that paper is to look a bit more carefully at something which I'm going to explore, which is a prediction. Well, not exactly a prediction, but basically from algorithmic probability, one of the sort of statements that's coming out of it is to do with, you can use it to make information theoretic sort of limitations on predictability somehow. But one of the things that comes out of it, which is kind of interesting, is that it also gives you cases where you actually might not be able to predict or when you kind of can predict. And one of the strange consequences that has been mentioned but hadn't been studied in practice is that sometimes you can have a time series, a deterministic time series, which is when you have more data, your ability or your confidence in predictions actually can go down. So not only more data, but more data that all conforms to the same trend, like 1, 1, 1, 1, 1, 1, 1, 1, 1. For certain special values of how many ones you have, it actually reduces your confidence in the predictability of the next bit, which is the opposite of what is normal sort of a common sense understanding. Anyway, so we're kind of playing with these areas, and it's sort of a new area, and we're trying to see if there's something interesting going to come out of this. And that is basically, that's it. So what are the main take-home messages is that probability and complexity in these sort of shapes, in these kind of areas, are closely connected. We can make, so algorithmic probability is this kind of topic which is sort of interesting and sounds a little bit out there, but somehow people are kind of excited by this, some people, and we're trying to get a sort of a research momentum going. And we actually have we work with Boumediene on this and Marcus Hutter in Google DeepMind. Simplicity bias is basically a sort of a real-world applicable form that we can actually use in various contexts with things that we can actually compute and calculate. And it's interesting for two reasons. One is a kind of philosophical or scientific reason, which is a kind of what has been the focus of my work before, which is that it gives some kind of explanation for why simplicity or why symmetry is somehow maybe favored or appears more often than you might expect in nature. More interesting perhaps to this community is the kind of the practical thing, which is, okay, we can maybe use it to predict probabilities in a totally different way as to what we normally do, which is just to directly look at them, work out their complexity rather than doing like sampling or something. And finally, sort of the direction that we're trying to go in is to try and look more at algorithmic information theory and algorithmic probability and how they can contribute to dynamical systems and machine learning. So yeah, thanks for that. Okay.